Hello and welcome to Chapter 3 on minerals. Now the picture that you're looking at here is a large cave in Mexico where we have these exceptional crystals of gypsum, more particularly a variety known as selenite. Now you can see that the people here, they are wearing like these hazmat suits and respirators. This cave does have exceptionally high temperatures, potentially some toxic fumes within it, and so they can only stay in there a few minutes. But it's the unique properties, the unique environment within that cave that allows these giant gypsum crystals to form. Now, the basic outline that we'll be going through, we'll be looking at the definition of what a mineral is, and so what is and is not a mineral. We'll talk about properties of minerals, ways to identify them and distinguish one from another. We'll talk about the silicate minerals, which are made by the silicon-oxygen tetrahedra, and how those are the most important rock-forming minerals. Now, the crystals that you're looking at on the screen, these are some nice crystals of quartz, which is a exceptionally common mineral. You've probably seen it in a few rock shops and other places. Now, there are thousands of different minerals out there, somewhere between 3 to 5,000, depending on how you try to count them. What you consider to be a unique mineral versus something that's just a variation of something else. But there's minerals that have a lot of important industrial or commercial uses, like making sheetrock. So those gypsum crystals that we saw, the most important use for gypsum is, well, it's called sheetrock or gypsum board, drywall, whichever. Also, other minerals are used in making concrete, various chemicals. We use copper and wiring, of course. Many more pretty versions of certain minerals are used for jewelry and so forth. Now, there's lots of minerals that are beneficial. Some have interesting economic value. And then there's some, like asbestos, that can be harmful. Now, the crystals that we're looking at here now, these are crystals of, should be rhodochrosite, which is not exceptionally common, but you will occasionally find it in some rock shops, just usually not quite as pretty as what we see here. Now, the definition of a mineral, minerals have to be naturally occurring, they have to be inorganic, and so no organic material there. Again, we're talking about organic in the chemistry sense, not the Whole Foods Market sense. We'll talk about that in a moment. It has to have an ordered internal structure. So in other words, it has to be crystalline. So like these quartz crystals here, these are quartz crystals that have been chemically treated. They have been covered with a very thin coating of, should be titanium, and that's what kind of gives us this weird iridescent color in this case. So chemical, definite internal molecular structure again, so in other words, crystalline, and it has to have a definite chemical composition. And so if it fits those points of the definition, then it is a mineral. If it does not fit any of those points, then it is not a mineral. Now, if we consider some of the different materials, let's consider something that is a mineral first. So, for example, table salt, also known as halite, the sodium chloride, whatever. So table salt is naturally occurring, and so it fits that point in the definition. It is inorganic, and again, we're talking about organic in the chemistry sense, not the Whole Foods Market sense. It has an ordered internal structure. So if you look at salt crystals, salt grains really close up, you'll see that there are a whole bunch of tiny cubes. They're cubic crystals. And it has a definite chemical composition. And so it has that composition of sodium chloride. And so table salt fits every point of that definition. And so therefore table salt is a mineral. We call it halite. Halite is the mineral name for table salt. Now, if we look at some other things that we might find in the kitchen, just try to decide if they're a mineral or not. So first off, let's say sugar. So sugar is also naturally occurring, but sugar has an organic composition. So sugar fails one point at the definition there. Now it is still crystalline, and so you will look at sugar really close up through a magnifying lens or a microscope. You will see that it is forming little crystals, and it does have a chemical composition that's definite, and so it fits most of the points except for, again, the fact that it's organic in origin. Now, again, we're talking about any sugar in the chemistry sense of organic, not the Whole Foods Market sense. So it doesn't matter whether Whole Foods Market calls it organic sugar or not. Chemistry-wise, all sugar is organic because it has a composition that's mostly carbon bonded with hydrogen, and then most organic compounds also typically throw in either oxygen, nitrogen, or a whole bunch of other things. And so if it is something that they would discuss in organic chemistry class, then it would not be a mineral. Okay, so let's look at a couple other things. Let's say ice. Would ice be a mineral? So let's look at the various points. Ice is naturally occurring. It is inorganic. Now, some people may kind of trip up on that one a little bit because we know that water is necessary for life as we know it, but water in and of itself is not organic. Because again, organic chemistry always involves carbon and it's always bonded with hydrogen and then typically also oxygen and nitrogen. And so unless you have that going on, it is not an organic compound. And so ice of itself is not organic. It does have an ordered internal structure, and so for instance, snowflakes, the patterns that snowflakes make are just the intergrowth of different ice crystals form this really unique pattern. And then ice has a definite chemical composition, so H2O, that's its composition. So ice would be a mineral if you do not specify a temperature that it has to be solid at. If you say it has to be solid at room temperature, then that would rule it out. However, if you do not specify a temperature, then it would technically be a mineral. Okay, so ice would technically be a mineral. Salt is a mineral. Sugar is not. Let's consider actually two more examples. So first off, let's talk about coal. So coal is naturally occurring. However, even though it is a solid, it is not inorganic. It's actually organic in origin. And so coal is just really highly compressed dead swamp plants. That's all it is. And so it is organic in origin. It is organic in composition. It's mostly carbon. You still have some of those oxygens and hydrogens, nitrogens, etc. still in there. And so its composition is technically still organic. Also, coal is not crystalline, so it actually fails 2 points of the definition there. So coal is not a mineral. Even though the mining industry will often call it that, again, they'll call anything a mineral as long as they can dig it out of the ground and sell it. But in a geology class, no, it is not a mineral. Okay, so let's look at one more example. So what about diamonds? Are diamonds minerals? And so a lot of people get mixed up because of what we just said about coal. But if we look through the things first, try to decide. So first off, diamonds are naturally occurring. So let's switch that color back there so that we have that. So diamonds are naturally occurring. They are solid. Now, a lot of students and a lot of people get mixed up by whether or not diamonds are organic. Now, the trick is diamonds of themselves, they are pure carbon. There's no hydrogen bonded to them, no oxygen or nitrogen. So the other things that we see for organic chemistry are just not there. It's pure carbon bonded to itself. So as far as chemistry-wise, it is not organic. Also, a lot of people get mixed up about where diamonds come from because there's a myth that's been circulating for generations about diamonds coming from coal, and that is a myth. Diamonds do not come from coal. Diamonds come from the mantle. They originate in the mantle because that's where the temperatures and especially the pressures necessary to get to diamonds occur. And so we don't find diamonds in coal beds. In fact, coal beds are younger than the rocks that contain most diamonds. And so diamonds originate in volcanic rocks where you have rocks that came up from the mantle and included a lot of these diamonds in them that formed much deeper below the surface of the earth. So diamonds do not come from coal, they're not organic, and so therefore they fit the definition. They have a very ordered internal molecular structure, they are crystalline, and they have a definite chemical composition. So again, they are pure carbon. So diamonds are minerals, even though coal is not, and diamonds do not come from coal. Now, this myth, maybe it originated back with the Superman comics. I know it made several appearances in the comics and the TV shows, etc., for Superman, where in several instances, Clark Kent needed a last-minute gift for Lois Lane, and being Superman, he just took a lump of coal in his fist and squoze really hard, and then gave her a bunch of loose diamonds. So, yes, it's technically true that if you take any source of carbon, whether it's organic or not, but it's tricky to find any carbon besides diamonds that is not organic. You have diamond and graphite, and that's pretty much it. But if you take any source of carbon and replicate the conditions in the mantle, and so we're talking about the temperatures and the pressures especially. If you can replicate the conditions in the mantle and expose any carbon to that, you can form a synthetic diamond. In fact, there are several companies out there that will do that now. Some of the more notable ones will do that with, well, they call these memorial diamonds. Others will call them cremation diamonds, because basically what you do is you take a sample of a deceased loved one's cremated remains, send it to this company in the mail with a very large check, and they will turn a portion of those cremated remains into a diamond for you. Some people really get excited about the idea. Others think it's really weird. I'm a little more in the weird camp, but anyway. Yeah, it doesn't have to be cremated remains. Basically, you can take any source of carbon and get a diamond made out of it. Now, so anyway, we should have the basic definition of a mineral there. We discuss some things that are minerals and some things that are not. So let's go ahead and turn the camera off so we can see the rest of the slide there. It looks like I can't do that, so we'll have to duplicate this. Okay, so now we're looking at the definition of a rock. So a lot of people get confused about the difference between rocks and minerals, but basically, a rock is composed of minerals or mineral-like substances. So while coal is not a mineral, coal is a sedimentary rock. And so other rocks, of course, we have granite that makes up the continental crust that's made of quartz, like we see here in this picture, along with feldspars and other minerals. We have basalt that makes up the oceanic crust that does not have quartz in it, but does have amphiboles and pyroxenes and olivines and things like that. Now, to understand what we mean by an ordered internal structure, that crystalline structure, it helps to kind of look at some of these repeating tessellating patterns made by M.C. Escher and other artists. So if you just imagine each of these shapes and colors being a distinct element, how they bond to each other will create a distinct pattern, and that is part of the crystal structure. So here's one example using just two colors of the same shape. Here's another where we have some more colors. And then here's another, again, three different colors and shapes. But again, if you just imagine this repeating, sometimes in 2 dimensions and other times in 3 dimensions. And so here we see the crystalline structure of two different minerals. So on the left, we have quartz. Now the red dots there, those red spheres, those are oxygen atoms. The little blue spheres you might see inside that other structure, those are silicon. And so basically just have that repeating pattern of oxygen and silicon. In the biotite, which is one of the mica minerals, you still have the oxygen with the red, and then the blue silicon is there, and then we have some other stuff, aluminum, and then many other elements as well. And it has a very different structure based on how all these different elements will bond with each other. So for quartz, because it's more of the same structure all the way throughout this complex three-dimensional framework, it has very uniform properties throughout. But for the biotite, because we have these weird sheet structures with some layers that have very strong bonds within the sheet, and then you have another sheet, but in between those sheets are much weaker bonds. That tends to be where the mineral breaks. And so that's one of the distinct properties of biotite, muscovite, and some of the other mica minerals. Now, as far as how minerals form, we have solidification from a molten material. And so a great example is just water freezing to ice. And so this is how, for instance, most igneous rocks form, or more precisely, how the minerals in igneous rocks form. They're molten, they cool down, basically they just freeze. It's exactly the same as a freezing process. The one difference is that for water freezing to ice, it's just one compound, just changing state. For a typical lava flow, you're having lots of different minerals mixed in that might crystallize at slightly different points. And so it's more of a longer process than just one freezing on its own. Now, then there's the second one, so precipitation from a solution. And so if you imagine, for instance, you dissolve a whole bunch of salt into water, and then you evaporate the water, or you do some kind of chemical reaction that will force some of the dissolved material to precipitate out. That's how a precipitate forms. So halite or rock salt is an example of one of these precipitates. Calcite often forms through a chemical reaction and precipitates from that. And then for the last point on the slide, the solid state diffusion. We'll get to this when we talk about the metamorphic rocks, because that's predominantly where it happens. But this happens in the solid state. And so basically, the structure for the particular mineral is no longer stable at those specific temperatures or pressures. And so it will just alter or change into something else. So it does not melt during the process, it just reorganizes itself. Now, this picture probably portrays better than any other why I don't consider myself a rock hound. The problem is most of the stuff that still impresses me is so rare that I won't ever be able to find it because it's only found in one or two localities on Earth. So for instance, these green crystals here, these beautiful green crystals, these are not emeralds. This is actually a very rare form of garnet called uvarovite that I believe is only found in maybe one or two localities in Siberia. So not the easiest place to get to, not the easiest mineral to find, and very rare. And because of that rarity, well, it's expensive. And so the stuff that's left that still impresses me way out of my price range. But looking at a few definitions for, well, chemistries. Now, just to kind of hold on, don't get too panicked about the chemistry definitions. We'll just highlight some of the more important parts. But in chemistry, especially with these minerals, we're talking about different ions. So this is an atom that has a charge to it. So either a positive charge or a negative charge. Now, if it has a positive charge to it, we call it a cation. And if it has a negative charge, we call it an anion. So typically we see different metals becoming the cations, and then we have other things that are the anions that bond to them in various ways. Now, most mineral groups, we'll look at this in a minute, but most mineral groups are categorized based on what the anion is in the whole structure. Now, if it's ionically bonded, you have the cation bonded to the anion just because of the difference in charge. So they're just trying to balance out the charges. And this is a very common bond. However, it's not always the strongest bond. Ionic bonds are, well, they can break apart if something comes along that's more attractive. So it's not typically a long-term thing. Well, long-term in the geologic sense, I should say. And so it's more likely to suffer through chemical alteration, dissolution, or just oxidation or other things if something more attractive comes along. Now, covalent bonds, on the other hand, these tend to be stronger. You have the sharing of electrons, everything's more balanced, and we'll take a look at that structure in a minute. And so water, for instance, water has covalent bonds. Now, a compound is the chemical combination of any two or more elements that creates something that has really distinct properties from whatever you start off with. Now, salt is a great example of one of these compounds that has different properties than what its constituent parts is. And so table salt is sodium chloride. So sodium in its pure state is a metal that is actually a little dangerous to work with. If you take pure sodium and put in water, it will actually explode. However, the chlorine, on the other hand, pure chlorine is a gas. In fact, is very dangerous as well. It's very reactive. And in fact, chlorine gas was used as chemical warfare, most notably in World War I, although it has made a few other appearances since then. But its use in World War I, its effects were so horrific that most nations after that deemed its use to be a crime against humanity. And so it was outlawed, even though a few dictators have still used it after that. Now, looking at an atom again, here we have in the center, we have the nucleus. Again, it's made up of protons that have a positive charge to it, and then the neutrons that have no charge. Now, with the protons having a positive charge, you have circling around the nucleus the electrons that have a negative charge. If the number of electrons and protons are the same, the charge is balanced out, and well, it's kind of a stable makeup like that. However, if there are more protons, there's not enough electrons orbiting around, then there'll be a positive charge and it'll be a cation. If there are more electrons, then it'll be a negative charge and we call that an anion. Now, for reasons that are a little more complicated than what we'll get into here, that would be a good question in a chemistry or physics class, different elements want the outermost orbital to be either completely full or completely empty. And so here we can see in this orbital there are 1, 2, 3, 4, 5, 6, 7, 8 electrons in that orbital, in that third orbital. And so let's say we had an instance where there were, say, 2 missing. And so if it still bounces out with the number of protons, again, there's no charge to it, but it wants that outer orbital to be full. And so if it can steal 2 electrons from somewhere else, that outer orbital will be full, but then it'll have a -2 charge to it. Let's say, on the other hand, that we have a atom that just has 2 two electrons in that outer orbital, and it wants to have 8, it's easier for it to give those 2 electrons away rather than get 6 more. And so typically we'll lose those probably to something that wants to. And then it would have a +2 charge because there'd be 2 more protons than would be than in the electrons. Now looking at halite, halite is a great example of a mineral that is ionically bonded. So we can see here that the chlorine ion has a negative charge to it, so you can see that little symbol there. So the chlorine has that negative charge to it, while the sodium has a positive charge to it. So they're attracted to each other just because of difference in charge. And so opposites attract, at least in chemistry. That doesn't always work for people, but in chemistry it works. However, if something else comes along that is as attractive or more attractive than what it's already bonded with, those bonds tend to break apart if it's ionically bonded. Now here we see that with covalent bonds, that electrons are being shared. And so if we have 2 atoms that are both lacking 1 electron, instead of one stealing the other, then again, if that were to happen, one would be complete, but then the other would be lacking 1. But they can both share 1 each, then they're essentially both sharing 2, but they're both complete, they're both full. And so it's kind of like that line in that old Jerry Maguire movie, "You complete me." Again, it's a very stable arrangement. It does not tend to break down very easily. It's much stronger than what we see for the ionic bonds. Now, looking at the different classifications of minerals, these are mainly classified by what is acting as the anion in the structure. Now, first off, though, we're going to look at one that does not have one of those anions, and so those are what we call the native metals. And so these are metals, or actually other elements as well, that can exist in their pure state in nature. Now, a great example of a native metal is, of course, gold. So if you think of gold nuggets, again, that is an example of a native metal. You can also get pure copper in nature. We'll look at an example of that in a second. Now, other examples of elements that can exist in their pure state, we have, of course, carbon with diamonds and graphite. And then there's also sulfur, which is the crystals that we see here. Pure sulfur forms these really brilliant yellow colored crystals. They're really quite distinct. Now, looking at some of the other mineral groups, the halides, we take one of the halogen gases like chlorine or fluorine. Those are acting as the anion. And so you combine either chlorine or fluorine with any number of metals and maybe something else in there, and you get one of the halide minerals, like rock salt, which is also known as halite. And then there's fluorite. We'll look at examples of both of those. Now, oxides, of course, it shouldn't be too hard to figure out what is acting as the anion here. It's oxygen. And so basically, the oxides are just different examples of rusted or corroded metals. And so we have, of course, hematite and magnetite. These are 2 examples of oxides of iron. Now here's an example of native copper. So copper can exist in its pure form in nature, but if it's exposed on the surface for too long, of course the copper will start to oxidize and it'll kind of turn this green color. So you might have seen that if you've ever encountered some really old pennies, how they will sometimes change color that way. Not just the dirty tarnish, but if they actually start to turn green, that's just the copper oxidizing. Now here we have an example of halite. So again, remember halite is just the formal mineral name for rock salt or table salt. And again, it's halite is a prime example of one of the halide minerals. Now here we have some more examples of halite. So again, here's some better crystals. We can see that when we have a full crystal, it is cubic, although we can have several crystals kind of intergrowing with each other as we see in both of these examples. And here we have another halide mineral. This is fluorite, so it's calcium fluoride. And it also forms cubic crystals, but the composition is very different, of course, and some of the other underlying factors of its structure are very different. Fluorite, the other notable thing about fluorite, besides its structure, which we'll look at some aspects of that later on, is that it does come in many different colors. You will find fluorite that's purple, clear colorless, various shades of blue or green. It can come in a wide variety of colors, but it's not the only mineral that does that. So looking at other minerals that do come in many colors, of course, there is corundum. Now, corundum is just the name of the mineral. However, if it's kind of a reddish variety like this, then we call it ruby. And so ruby is just the gem quality version of corundum that happens to be red. But all corundum is just aluminum oxide. And if you can take a sample of aluminum or alumina, so it's kind of the partially oxidized version of it, you can actually make synthetic rubies if you have access to an arc welder. There's actually a few YouTube videos I've encountered recently on how you can actually do this in your own garage. Again, if you have the right equipment and you know what you're doing. But looking at some other minerals, of course, there are several other groups. But first off, we'll look at the sulfides and the sulfates. Now, in both of these groups, it's sulfur that is involved. For the sulfides, it is sulfur in a -2 charge, so it has 2 extra electrons that gives it that negative charge. And then you combine that with various metals to balance out the charges and so on and so forth. The sulfates, though, you combine the sulfur with 4 oxygens first. It still has a -2 charge to the group, and then after that you combine it with various metals to get the different sulfate minerals. But we'll take a look at the sulfides and the sulfates in a minute. Sulfides include many important ores like pyrite and galena. Galena is the main ore for lead. Pyrite, kind of a mediocre ore for iron, but we'll talk about that a little later on. The silicates are the most important rock-forming minerals, and so they're combining a silicon atom with 4 oxygens. Actually should have an minus charge on that, -4 charge, I believe. And then there's the carbonates. So you combine carbon with oxygen. Now, there's no hydrogen or anything like that involved, so it's not organic in the chemistry sense. But we take those carbonate groups and combine them with any number of metals, and then we get one of these carbonate minerals. And so a great example is calcite, which is calcium carbonate. I'll take a look at some of these in just a second. So first, looking at some of the sulfides. So galena is a lead sulfide. It tends to form cubic crystals, but they tend to have a really kind of a silvery gray color to them. Now, the main diagnostic feature for galena is its very high density. It has what we call a high specific gravity. So the specific gravity is how dense a material is in comparison to an equal volume of water. And so most minerals have a specific gravity around 2 or 3. Galena, on the other hand, you're looking at about 10 to 11. So it is several times heavier, about 4 times heavier as most other common minerals. Now, skipping ahead to calcite, again, this is one of the carbonate minerals. So we have that carbonate group there, again, a carbon surrounded by 4 oxygens, and we combine that with some calcium and other stuff. And so if it's calcium involved, that becomes calcite. If it's magnesium and calcium, we call that dolomite. There are dozens of different carbonate minerals, but calcite is by far the most common out of all of them. Now, before we dive in on these silicate minerals, we have to understand why they are so important and why they're so common. If we look at the bulk composition of the continental crust, and so again, this is mainly the granites and so forth, the two most common elements by far are oxygen and silicon. And so after that, of course, we have all the other metals. We have 5 or 6 somewhat common metals that kind of round out most of it. But then everything else on the periodic table is less than 2% of the weight of the continental crust. And so most minerals in the crust, as well as the mantle actually as well, most of these are silicates. Silicate minerals, and we'll take a look at that and their structure and how the different groups of the silicate minerals differ. So first off, with the silicates, again, they're the most important mineral group because they form the vast majority of the rocks, especially in the continental crust, but the oceanic crust is also composed of silicate minerals. The mantle is composed of silicate minerals. You just have different groups of silicate minerals that are more dominant in each of the types. But the basic thing is that we have 4 oxygen ions surrounding a much smaller silicon ion. And so it creates this really distinctive structure that's very similar to this. So this might not show up particularly well on the camera there, this little toy we have here. But this is the best we could do without the chemistry little models that we have in the classroom. So we just have these magnetic little toys that are trying to symbolize that. But basically you have the oxygens at the corners, and then in the middle you have a smaller silicon ion. And so the structure looks very similar to this. Again, there's that smaller silicon atom in the middle. It's the cation, and then the oxygens are the anions. So it looks like the picture, the video picture is kind of obscuring that, but you can see the beginning of oxygen there. And so it forms this structure that we call a tetrahedron. So tetra means 4, and so it has 4 sides to it, 4 corners. And hedron just refers to a 3-dimensional shape. And so we have these different, let's get that on camera, these different tetrahedra, but the important thing to remember now at this point is that at each of the corners is an oxygen, and those oxygen atoms in between each other, they have covalent bonds. And so those covalent bonds are very strong. And so the structure of the tetrahedra is very stable, but you have to combine it with something else because it still has a negative charge to it. Now, the different groups of the silicate minerals will vary depending on how that basic structure of the silicon-oxygen tetrahedra are combined either with each other or with other groups. And so first off, we have the independent tetrahedra. Olivines, the real important one there, though we should also make note of garnets. Then we can start to form chains of tetrahedra, double chains, sheet silicates, which are the micas, and then more complex 3-dimensional frameworks. But basically, you start to get these more and more complex arrangements of how they are interlinked with each other. So let's take a look at a few examples. So first off, with olivine, Olivine is an example of a silicate mineral that has these isolated tetrahedra. And so by isolated, we're meaning that these tetrahedra are not directly linked to each other. They have to be linked to something else in between. And so here we have, just a cube to symbolize some other compound or element. And then you can combine some tetrahedra on the other side or wherever, but the tetrahedra are isolated from each other. And so that's what we mean by these. And so an important thing to remember for these isolated tetrahedra, especially as we look at olivine, is that they tend to be richer in more reactive metals like iron and magnesium, metals that tend to oxidize fairly easily. So we go from having isolated tetrahedra in the case of olivine to start to form chains, which is what we see for pyroxenes. And so what we do is you combine them by sharing an oxygen that's at the corners of these tetrahedra. And so once you start to do that, remember that within the structure, in between each of the oxygens within each tetrahedra, you have covalent bonds. But now that you're sharing oxygens, you have just a whole bunch of covalent bonds throughout the entire chain, and it's much more stable than having just isolated tetrahedra. So you go from that to something that becomes just a little more complex. And so you go from a single chain to what we call a double chain. And so hornblende, which is one of the amphiboles, this is an example of one of these double chain silicates. And then again, remember you have the pyroxenes like diopside and so forth that have the single chains. And so you start to get more and more complex arrangements, and that's what we're getting at. And so you go from isolated to single chain to double chain, and then you can go from the double chain to sheets. But first, again, looking at a couple of examples, here are some nice hornblende crystals. Again, this is in the amphibole group, so the ones that have the double chains. Now, as you start to get more and more complex arrangements of tetrahedra, you start to use up the iron and magnesium. You start to move on to different metals that are maybe not as easily oxidized as those. But in this case, you start to get a little bit of aluminum, especially as you go further down this reaction. Okay, and now we get to the sheet silicates. And so we have these tetrahedra that are arranged into sheets. And again, remember that these tetrahedra are bonding with each other by sharing oxygens at the corners. And so it's a very stable, durable arrangement. And there's covalent bonds throughout the entire structure. Now, there are covalent bonds throughout the entire sheet. And so it's a very durable chemically and mechanically as well. But in between the sheets, you have stuff that has weaker bonds. And so if the mineral is going to break, it is going to break in between those sheets. It's going to peel apart into relatively thin sheets. And these are what we call the sheet silicates or the micas. And so on the screen, we're looking at muscovite mica. Again, it's one of the common mica minerals. The other common one is biotite. And then there's a few others, but those are the two that you will hear about the most. Biotite tends to be dark brown to black. Muscovite tends to be kind of a tan or clear yellowish color. Okay, so from there, once we get to the sheets, we start to arrange these into a more complex three-dimensional framework, which kind of goes beyond how many of these little magnetic toys I have at my disposal. But basically, you start to form this complex three-dimensional framework, but you still have lots of other metals in between. And so for the feldspars, you will always have aluminum in there, but then depending on what variety of feldspar you have, if it's a potassium feldspar, guess what? You have potassium in there. If it's a plagioclase feldspar, you'll have some mixture of either calcium or sodium in there. So you can still have some potassium in there, so K is potassium, but then plagioclase will be more dominated by sodium and calcium in some ratio, depending on what specific variety of plagioclase you're dealing with. And so here's an example of a potassium feldspar. Potassium feldspars do vary in color a bit, like, well, many other minerals do. They can often be off-white, but sometimes you have this kind of a orange or salmon pink color. And so this is a potassium feldspar. And then here we have a plagioclase feldspar. Plagioclase can also be kind of an off-white. But then it can be various shades of gray to even almost black. Now, one diagnostic feature for plagioclase are these kind of faint lines that you see on the surface. They're almost perfectly straight and almost perfectly parallel with each other. Plagioclase will have that, but potassium feldspar will not. Instead, potassium feldspar will have these kind of wavy lines. They're actually, you can see that they are more inside of the crystal. Now, before we get on to quartz, we'll talk about a few other properties that can be helpful in understanding quartz. And so first off, there's what we call crystal form. So crystal form, we're talking about the shape of the crystal that is a reflection of the underlying framework of the crystalline structure. And so this is what happens when things are ideal. However, it's important to understand that oftentimes conditions are not ideal, because if you have, let's say, a mineral that grows after the others that it usually forms with, if it's coming afterwards, it usually just grows into whatever shape is left. Unless you have a really nice big open space like a geode that it can grow into. There can be other things like, again, just generally speaking, things may be happening too quickly, or there's just too much competition for space anyway, but especially if you have something that's coming after everything else, it just takes over whatever space is left. And so here we see a garnet. So this is a fairly good garnet crystal. And yeah, you will see that a well-formed garnet crystal will have these kind of, well, diamond-shaped faces. Technically, it's a rhombus, but if you have a good crystal, there will be 12 of them, although many garnets will have these kind of additional beveled edges between faces. Let's use a color that maybe pops out a little better. No, unfortunately, nothing's really popping out on that darker surface. But garnets, good, well-formed garnet crystals will have the 12 sides, but there can be those beveled edges to them. Now, the difference, we need to talk about the difference between what we call crystal form and crystal habit. Crystal form is the kind of idealized shape of that particular mineral. And so here we see the distinction between the crystal form on the left here. Again, that's the idealized shape of that particular mineral. And then, well, the habit is just what usually happens. Now, the distinction, the comparison that I'm trying to make here is the difference between, say, Barbie dolls and real people. There is a difference. And so again, on the left, we have, again, the Barbie doll example. We have what all the fashion magazines tell us we're all supposed to look like. But on the right, we have something that, well, what real people look like, what people who've actually had a good meal recently really look like? So yes, there is a distinction, but we need to understand that especially when we look at these idealized samples that we like to show in class or in textbooks or whatever, most samples don't look anything like that. Again, those are the idealized samples, not the most common. Now here we're looking at a couple of examples of some well-formed crystals. On the left, we do have some really well-formed amethyst crystals. We have this nice amethyst geode here. And so again, it had this nice open spot that it could grow into. And so that's why those quartz crystals were able to form so well. So amethyst is just the purple variety of quartz. On the right, we have some very well-formed pyrite crystals. So you may know pyrite as what's commonly referred to as fool's gold. So pyrite can form cubic crystals, but can form other shapes as well. And so it's not uncommon for pyrite to form crystals that have pentagon-shaped faces and have 12 faces to it. And so there's two really distinct crystal forms for pyrite. So it can be cubic, as we see on the right. It can be 12-sided, as we see on the left. Now, not to be too confusing, remember that garnets also have 12-sided crystals. Now, these are totally different, though, because the faces, there's 4 sides to the face. It's a rhombus shape. Whereas on the pyrite, let's see how well I can trace that. On the pyrite, there's 5 sides, and so they're pentagons. And so even though there's the same number of faces, the underlying geometry is just totally different. And so, yes, the number of faces, yeah, that can be distinctive, but you have to look at the shape of the faces, the angles between the faces. Sometimes it's more indicative of what you're really looking at. Okay, now here we have Mohs hardness scale. Mohs hardness scale is a ranking of minerals according to hardness. Now there's actually several different ways you can portray hardness, such as how well it resists denting, how well it's able to be shaped. But Mohs hardness scale is a look at how well different minerals resist scratching. Now on the soft end, we have talc. Talc is the softest mineral. And then on the hard end, we have, of course, diamond. Diamond is the hardest material. Now, occasionally you will see some news reports that some scientists have created some new material that's even harder than diamond. But usually if you look down a little lower down on the article, you'll see that there's a little disclaimer that, oh, this is based on some simulation, because we can't make enough of this new material to actually physically test the hardness. And so basically I say to that, well, if you can't physically test the hardness, if you can't make enough of it to actually do something with it, it doesn't really matter how hard it is, does it? And so of the material that we have actually enough of it to do anything with it, the hardest material is diamond. Now looking at some of the different minerals in between, you will also see that there's some materials off on the right that we can use to compare the hardness. Now these are just a handful of handy materials, but if, for instance, it's soft enough to be scratched with your fingernail. If it's that soft, you know it's around a hardness of 1 or 2, and so you're looking at something like gypsum or talc or something that has a similar hardness. A copper penny, so copper has a hardness of 3, which should be about the same as calcite. And so calcite and copper, their hardness is roughly equal. Fluorite, remember that fluorite can come in many different colors, including purple. So does quartz. We looked at amethyst. But you can clearly tell the difference between the two just by looking at the hardness. Quartz is very hard. There's only a handful of materials that will scratch it, whereas a lot of moderately hard materials will scratch fluorite. Now, again, that's in addition to differences between their crystal form and some other properties. Now, one thing that we do see, again, is looking at quartz. Quartz has a hardness of 7. And now we already mentioned amethyst, how amethyst is just purple quartz, and amethyst is considered a semi-precious gemstone. So it is used in jewelry, but it doesn't command the same high prices as, say, diamonds and rubies and emeralds and so forth do. And if we look at where some of these more valuable gemstones fall in on Mohs hardness scale, getting a little ahead of myself, if we look at where they fall in on Mohs hardness scale, we do see a trend. And so first off, harder than quartz, we have topaz, which is used for jewelry. It's still usually considered a semi-precious gem for several reasons, but again, harder than quartz, usually considered a little more pretty than quartz if you can find some really great topaz. If you haven't heard, you can collect topaz yourself here in Utah down at Topaz Mountain out in the West Desert. Now, harder than that, we do have a few others now. We already mentioned corundum. So corundum, you might remember if you have gem quality corundum that is reddish in color, we call that a ruby. If you have gem quality corundum that is blue or mostly other colors, we call those sapphires. And so 9, we have rubies and sapphires. Around the same hardness, so kind of in between the hardness of topaz and corundum, we have a mineral known as beryl, that's spelled B-E-R-Y-L, that, again, you've probably never heard of that mineral, except when it's a really pretty green color, and then we call it an emerald. So you can see that harder than quartz, we have topaz, emeralds, rubies, sapphires, and then of course getting up to 10 we have diamonds. So why would the precious gemstones all be harder than quartz? And it's not necessarily hardness that makes them prettier, it's what keeps them prettier. And so you can find really pretty examples of basically any of the other minerals, either on Bowen's reaction series, Mohs hardness scale. Keep getting a chapter ahead of myself there. Mohs hardness scale, or any of the thousands of other minerals out there. But it's only the ones that are harder than quartz that typically wind up being used extensively for high-priced jewelry. And the reason why, quartz is extraordinarily common. Now, that is not what makes it cheap, although that doesn't hurt, but the fact is quartz is almost everywhere. Most sand, at least on the continents, is quartz sand. And so you will have quartz in the sand, you'll have quartz in most soils. Quartz is almost everywhere, at least on the continents anyway. And so if you're going to spend thousands of dollars on a really expensive piece of jewelry, you don't want something that's going to get scratched up as soon as it touches anything. And so that is one reason why, again, diamonds are such valuable gemstones, although, well, there's a little bit of market manipulation there. But the only thing that can scratch a diamond is another diamond. There's only diamonds and 2 or 3 other minerals that can scratch rubies and sapphires. And again, that's why some of these harder minerals are the ones that wind up being gemstones when they are pretty enough, because again, once you get them cut and faceted, they hold their luster very well because they don't get scratched too easily. You can find beautiful, brilliant examples of gypsum and calcite and some of these other minerals. However, they get scratched too easily, and so they don't wind up being used in jewelry the same way that diamonds or sapphires are. And so when you use some of those softer ones, you have to just take a thin slice of it and then mount something hard on top of it, like a clear piece of quartz or a white sapphire or whatever. But once you get up to white sapphires, well, why would you not just use the sapphire? And that's the trick. And so is the harder minerals that wind up in the jewelry when they are gem quality. When they're not gem quality, their hardness is used usually as abrasives. The vast majority of diamonds out there are not gem quality. The vast majority of diamonds wind up as industrial diamonds, where they're used for grinding tools, um, drill bits for drilling into rock for like the oil industry, etc. Now, some other properties of minerals, we have luster. Luster is just the way that a mineral reflects light. And so usually we try to decide whether the luster is metallic, whether it looks like a nice shiny piece of metal, or whether it looks non-metallic. And so other terms for some of these non-metallic luster include glassy, for it looks shiny like glass. We can call it glassy, or vitreous. There's silky, earthy, waxy, pearly, dull. These are just a number of the more subjective terms for different types of luster. But usually we try to decide whether it looks metallic or non-metallic. Galena is a great example of a mineral that has a metallic luster. Now, there are some other physical properties of minerals such as color. Now, color, the biggest thing that we should see about color is that it is not really reliable for identifying minerals. Remember that in the example of fluorite and amethyst, again, the purple quartz and then the purple fluorite, yeah, they're both purple, and so a purple color is not really that diagnostic. With thousands of different minerals out there, there's always going to be something else that is the same color as what you're looking at. And so color can be helpful, but is often unreliable. So one, there's dozens, if not thousands of minerals that happen to be the same color as something else. Two, there's lots of variation in color. So remember that fluorite comes in many colors, quartz comes in many colors, as we'll see. Garnets, corundum come in many colors. And so it's not reliable. Helpful, but very unreliable. So here we're looking at two examples of garnets. So on the right, we have the more typical example of a garnet. That's kind of a reddish, brownish, purplish color. But remember that garnets can come in many colors. And so this should be another example of that uvarovite garnet. There's also tsavorite, which is another different shade of green, and almandine, which is usually another shade of green. Garnets come in many different colors. Greens and reds tend to be the most common, red the most common by far. I have heard of some even more exotic colors for garnets. I've just not seen them personally. And then there's quartz. Quartz comes in virtually every color. Now, most quartz that you come across will usually be just kind of a colorless or an off-white color or light gray. The off-white to white color, we refer to that as milky quartz. If you have various shades of gray, they call that smoky quartz. And then, of course, the amethyst, as we already mentioned, that is the purple stuff. The various shades of yellow to brown, they call that citronelle. And then there's also pink quartz, which they call rose quartz. And then there's also various shades of orange, blue, red, and green quartz. which is also out there. I do not remember the specific color names for those because it just shows how often I even see them. But they do exist. I have seen a few examples of some of them, usually in museums. Now the trick is also with quartz, and we see this for several other minerals as well, especially some gemstones, they can change color. And so if you have a piece of milky quartz and you expose it to certain types of radiation, it turns black. And so this basic process has been used, for instance, for medical badges, well, safety badges for workers in nuclear plants. And so they embed a little piece of either quartz or some other material that does the same thing when exposed to certain types of radiation. They may embed that in their ID badges. And so if somebody's ID badge ever changes color, that particular worker gets some mandatory time off, if you catch my drift. And so again, that's just one way that these can change colors. Another is with topaz. Out at Topaz Mountain, if you look at any of the topaz you just find on the surface that have already weathered out of the rock, those are all either colorless or white. However, the more valuable color topaz, there's some really interesting kind of pinkish topaz that you can occasionally find out there. You will never find those on the surface because if they are exposed to sunlight for too long, they lose their color. And so to find any of the pink topaz, you have to start busting open lots of rock and hope you get lucky. But if you ever get it cut and faceted and put in a piece of jewelry or whatever, you can't wear it outside for too long. Now, again, that won't happen in just a matter of hours, but again, if you wear it often, you will eventually see it. It'll just totally change color and lose its color. And by doing that, it will often kind of lose a lot of value. There's also some other minerals that will do some weird color changing things. And so one notable one is alexandrite. So alexandrite usually is kind of a bluish color, but depending on what wavelengths of light it's exposed to, if you were inside where you're typically going to have more incandescent light or fluorescent light, it may look one color. However, you go outside with that piece of jewelry, the stone can look a totally different color. It might be a little more purple, for instance. I bought my wife an alexandrite ring, so one that had the synthetic alexandrite stone because it was significantly cheaper than the natural stone. But I bought my wife that alexandrite ring, and again, most of the time is kind of a blue color, sometimes under some lighting is a little purplish. And then one time on a trip, she just happened to be wearing that alexandrite ring on the plane, and then she was sitting by the window seat and she noticed that the alexandrite stone actually looked a little green. And so whatever wavelength of light is more prevalent at higher altitude will totally change the color of the stone. And so, yes, color can be helpful, but it can look totally different depending on what light you're looking at under. It can change color temporarily or permanently. And then there's many minerals that are the same color as something else, and many minerals that come in a huge range of colors. So color can be helpful, but oftentimes is totally unreliable as a way to identify a mineral. And so we mentioned corundum before. Now corundum is just that aluminum oxide. And if it is the prettier variety, if it's a kind of a prettier blue, again, we call those sapphires. If it's a prettier red, we call those rubies. So rubies and sapphires, just the prettier color of corundum. There are some other color phases, not as well known, but most of the other colors, they're not distinct enough to have their own name. We just call most of the other colors sapphires, even though we associate sapphire with those really nice blue ones, like we see on the screen there. Now, because corundum is a hardness of 9, it's fairly hard. It's really easy to synthesize. And so most non-gem quality corundum, whether it's natural or man-made, if it's not pretty enough for jewelry, it just winds up as an abrasive. And so you might see on various grinding wheels and various other abrasives that they're just simply labeled aluminum oxide. Basically, that's exactly the same thing as a ruby or a sapphire. It's just not pretty enough for jewelry. Okay, now some other properties of minerals. Of course, there's what we call streak. Streak is the color of the mineral once it is powdered. And so we use a small tile of unglazed porcelain for this. And well, basically, it's usually very similar to the color of the mineral itself, although not always. Sometimes you can be seeing a drastically different color than the color of the mineral sample itself. We already kind of touched on hardness a bit. And so again, we're looking at resistance to scratching, and it's ranked on Mohs hardness scale. And so these are two really great properties to look at for identifying minerals. And then there's what we call cleavage. Now, cleavage is the way that a mineral will break. Now, remember that if there's any areas where the bonds are weaker, any distinct directions where the bonds are weaker, this is where it'll break, and it tends to be in really distinct patterns. Now, sometimes you'll have a distinct number of planes, a distinct number of directions, and angles between those planes, whereas in other cases, you don't have distinct directions of weakness, and so you will not have any obvious cleavage. Now, a great example of a mineral that has cleavage that's really different and distinct from the shape of the crystal is fluorite. So remember that fluorite has those cubic crystals like we see there. So we have a whole bunch of intergrown cubic crystals there. But instead of breaking into smaller cubes like rock salt will, like halite will, fluorite, instead of having 3 cleavage directions that are at right angles, it has 4 cleavage directions. And these are relative to the corners of the crystal. And so you wind up with this 8-sided 3-dimensional shape. So there we see the cube representing the crystal shape for the fluorite, and then the octahedron, that 8-sided shape, that is what it breaks into. And so yes, you have these 4 cleavage planes, but you have a parallel cleavage plane on either side, and so you take the number of cleavage planes, you double that, that's how many sides the resulting cleaved piece of mineral will break into. And so fluorite really distinct from the shape of the crystal. And so here we see 3 great examples of different cleavage shapes. So on the left, we have that fluorite there. Then we have in the middle halite. Again, halite breaks into a cube, even though it started off as a cube, so nothing changes too much, it's just a smaller cube. Calcite, though, calcite is also really distinct because it does have 3 cleavage planes, just like the halite does, except nothing is at right angles. And so it breaks into this blocky shape, but it looks like it's kind of slanted, if you will. And so that is really distinct for calcite. There's only a handful of minerals that will do that. Okay, some of the other properties, of course, we have fracture. So if it does not exhibit cleavage, it has what we call fracture. Sometimes it will still break into certain patterns because these fracture surfaces can curve in distinct ways. We call that conchoidal fracture, but we'll see that in a second. And then there's specific gravity. So specific gravity, most minerals are around 2.5 to 3, so averages around 2.7 or so. But if you have something that's a lot heavier like that galena, that will usually narrow down what you're looking at. Now, conchoidal fracture, we see a great example of this for this large chunk of quartz. And so this is the way that glass breaks. This is the way that obsidian, which is volcanic glass that's used for a lot of arrowheads, it breaks into this shape as well. Now, various cultures have used rocks like obsidian and flint that have good conchoidal fracture to make any number of stone tools like arrowheads, knife blades, spear points, tomahawks or hatchets, you name it. But it's takes a lot of skill. If you've ever tried your hand at it, you realize that one, you better have a box of Band-Aids handy, speaking from personal experience, and that two, unless you already have a bit of practice, it's going to take a long time to get any useful stone tools out of this. Okay, so looking at the list of the main properties that we use, again, we mentioned color, helpful but often unreliable. A streak can be more helpful because, especially if you have a streak that is different than the color of the sample, that can really shorten the list of what you should be looking at. Luster, the way it reflects light. Hardness, again, ranked on Mohs hardness scale, how well it resists scratching. Specific gravity, how dense it is, so useful for certain ores for identifying them. Crystal form versus crystal habit, so what shape it takes. And then cleavage, what shape it breaks into. And then there's a few properties that are more handy for a small handful of minerals. Now, a great example is magnetism. If you have a mineral that is magnetic or has a high enough iron content, it will stick to a magnet. That really narrows down what you're looking at. And so magnetism, this usually only applies to some of the higher grade iron ores, and some of the titanium ores will exhibit any degree of magnetism. Reaction to hydrochloric acid, we'll post a little video on Canvas for that, but this is only useful for the carbonate minerals like calcite. Malleability, how well you can shape a particular material and have it hold its shape. So gold is malleable. That's one reason why gold has been considered so valuable historically, is because, well, you can shape it into jewelry and it doesn't tarnish. That also helps. And then there's some really interesting optical properties. And so here in this picture, we see an example of what we call double refraction. And so if you have a really clear piece of calcite and you put it over on top of something or on top of a diagram or text on a page, you will see a double image of whatever's behind it. And so that is fairly unique. Now that property has been used for instance, certain gun sites and bomb sites, especially during World War II, because if they could get the two images to either diverge or converge in a certain way, that would help with determining how far away the target was. So that was kind of helpful. Taste. Most minerals don't have a distinct taste. There's a handful that do have distinct taste. So the best example is halite. Ordinary rock salt does have a, well, it tastes like salt. It's really that simple. Now, aside from halite, there's only a small number of minerals that do have a distinct taste to them. Most of them I would characterize as unpleasant. So the basic rule of thumb is that unless you think it's salt, don't bother tasting it. Smell, some minerals, only a small handful, will have a distinct smell to them. These are usually the sulfates and sulfides, as well as pure sulfur. So if you have pure sulfur and if you breathe on it, it will react to the moisture in your breath, and it will generate some hydrogen sulfide gas, which is also known as the raw egg smell. Also, if you have powder, some of the sulfides or sulfates, you can also liberate some of that sulfur. make it react to moisture in the air and generate that hydrogen sulfide gas that way as well. And so certain sulfides and sulfates will make kind of a stink, literally, if you scratch them a certain way. And then there's elasticity. And so there's some minerals like the micas that can bend and flex and then spring back to the original shape. And so these are some properties that are useful for, again, usually just a handful of minerals. Again, unless you're actually looking at something like the carbonate minerals, doing an acid test wouldn't help. But in fact, on some of the others, again, something that might generate a certain smell if it reacts to some acids, that would be unpleasant. One way to make a stink bomb, although when I've tried it, I couldn't get it to work for me. Others have sworn by it, but whatever. Okay, so that should wrap up chapter 3. And so you should go ahead and do the homework for chapter 3 on Canvas.